So when here, so to use the example, if you take the flux, and I'll use some standard notation, lambda is wavelength and F isn't. So if we have a distribution of light that looks something like this, which would be the spectrum, the spectral distribution of, say, an A star, where this is something like 3,300 angstroms, and let's say this is something like 6,000. The filters that Morgan created, and this is important for understanding what spectroscopy is about, were one that sat in the U, one that sits in the B, one that sits in the visual, and then another was added that goes into the red. Okay? Now, if you only have these 4 bands or 5 bands, the only thing you can get is the relative amount of energy in these 2 bands. That's correlated with, but doesn't give you any information about the details of the spectrum. Okay? The reason that you want to know about the spectrum is that virtually all of the information that we have about celestial objects is recorded in the spectrum and not just in the overall amount of energy or its broad distribution. Let me give you an example. If you just have 4 filters, then the only thing you can do for defining these slopes, for example, to get something like, let's say, a temperature measure, is to take differences between these filters or ratios. Okay? That gives you a very, very crude measure of what's going on. If you're looking through an external medium, like the interstellar medium, well, you know from the image you were just looking at from Wolf-Rayet stars, the space between stars is filled with dust. And that not only radiates in the infrared, which is irrelevant if we're working from the ground, but it also scatters light. And if you put that in the line of sight, it's a fog. So if you've got a star behind it, a portion of this isn't just going to be suppressed, its colors are going to be changed. So having only this kind of information, that is the photometry, you're subject to whatever absorber or scatterer you have along the line of sight that's not associated with your source. There are ways of extracting the information, but they're limited and they're uncertain. Okay? Instead, the essential point that was realized very early in the business, actually in the 19th century, is that the appearance of the spectrum, if you put a grating or prism in front of the detector, your eye or a CCD, is a pattern of absorption and emission lines whose relative strengths may be affected by this intervening medium, but whose presence and form is not. That's the basis of spectral classification. So to use an example, let me switch screens here, provided I can find which screen it is. Okay, so okay, so you can see, I hope, the sequence of spectra.
Yes.
Okay, this is the basis of spectral classification, not the color distribution. Okay, in general, we throw that information away. It isn't, it just looks good when you're giving a public talk. The important thing is the presence of these specific lines. Now, these are stellar spectra. In this case, they're stars that are relatively compact on the main sequence. That is, these are stars that are in their first stage of nuclear burning, which are the bulk of the stars that you see in the sky because they have the longest lifetime. The presence of these lines signals both temperature and other physical conditions in the outer layer of the star. I'll try to explain some of that. But the classification is based on the presence of the lines and the complexity of the spectrum. So if you change the distribution of the light here, it doesn't change these lines at all. Their presence is a fingerprint. And the spectroscopy gives you that information, which, if you were doing filter photometry, would be the equivalent of each one of these color bands. So all of the information about the hydrogen line series, for example, in the violet, all of that would be schmutzed together in a single filter measurement. Same thing with the blue, the same thing with the V, with the visual. Okay? So originally, the classification was based only on the complexity, that the stars that were called type A were the ones that had the minimal number of visible lines in low resolution spectra, like these. The B stars had a few more lines. The G stars, for example, looked like the sun, and there were stars that were then classified, just going down in order of the alphabet, as M stars and K stars that showed band structures. Now, it was realized only at the beginning of the end of the 19th century and the beginning of the 20th that the stars that are called O and B were actually hotter than those that were called A and so on, that the order, this is something that always confuses introductory astronomy courses. The order of the lettering changed when it was realized that one set of lines was actually not hydrogen, but helium. And that in fact, in the stars that are called B and also O, there are lines of ionized helium, which means these stars are intrinsically hotter than the ones that don't show helium. That's why their spectral looks slightly more complex, because they show hydrogen and then a few other strong lines. As you go further down the sequence, you go from the hydrogen lines dominating to the presence of other lines, which turn out to be the metal lines of, for example, the iron group like calcium, manganese, iron, and nickel. And then as you go to cooler objects, cooler meaning their surface temperatures are physically lower, you also see molecules, which are missing in these hotter stars. All of this information and comes from spectroscopy and only spectroscopy. If you look at an M star, for example, one of the coolest in the sequence, the bands are going to affect the colors, but you're not going to be able to distinguish which ones are which. Okay? I hope that's making sense. So to go back then, is the whiteboard showing again?
You're still in the spectrum.
Okay. Yeah, this is the same problem that I have with teaching remotely, that the feedback is the equivalent of communicating with Mars.
Yeah, whiteboard is back.
No, thanks. So I don't want to overwhelm you with things like quantum mechanics. So maybe if this is okay, let me just explain what it is that forms a spectrum before we go into what you can get out of it when you're actually putting a spectrograph on a telescope. Is that okay? Well, hearing no
Yes, we've
objection,
been muted.
um, well, Ken, why don't you act as the guiding force here?
Yeah,
But I don't want to do something too simple. So if everybody knows how spectra are formed, we can go on from there. But if not, I'd be glad to explain something about what actually is going on here. What are you seeing in that spectrum?
I think we do know, but it might help to give us more information.
Okay, then the first thing I'll say is stars are not black bodies. No matter what it says in elementary astronomy books. The only thing that is a black body, and even that isn't a very good one, is an asteroid that, or the moon. In principle, a black body is a solid surface of uniform temperature that is radiating uniformly across the spectrum and that otherwise shows no intrinsic absorption properties other than a continuous absorption. The sun, for example, doesn't look like that. And what you were just looking at, these spectra obviously have absorption lines. So when we're talking about about observing a spectrum, let's use the example of a star. We're not only looking at, say, the stellar surface, but we're also looking at everything that lies above that. Okay? That
Mhm.
if you're sitting out here and looking down through this, you have a surface below which the density and the opacity is sufficiently high that you can't see deeper than that layer. And to use the example, because you guys are in San Diego, you know what fog looks like. Okay? The
Mhm.
optically thick surface is the one that you see ahead of you, always at the same distance ahead of you in a uniform fog. Okay? The optically thin part is simply that the path length between you and the point at which the surface has actually become opaque is sufficiently short that the photons can actually reach you. Okay?
Mhm.
It's the same thing when we're talking about a photosphere. The difference is that in the case of the Earth, when you're just standing at the surface, the density is uniform. But you also know that when you're looking up, you can see the stars. I mean, you were just talking about observing seeing the aurora by looking up through the fog. So there's a density gradient that goes from the photosphere and decreases as you go further up. This is just because the atmosphere is in a mechanical equilibrium under its own weight. It's compressing, and the lower layers happen to be both hotter and have to be hotter because there's an internal source if it's a star, and denser. Okay, and everything above that then is traversed by the light that's coming from the photosphere. Now, this layer has a composition that may be the same as the deep interior, but you don't know that. The only thing you can see is what you can look through. Okay?
Mhm.
Whatever it is below that is either completely different and you won't know it except for perhaps some theoretical model, or it may be the same composition, it may be homogeneous, and you can get some information about that by the fact that the layer above it is sufficiently transparent that it produces the lines that you're seeing in the spectrum. Okay, all of that is in a nutshell, what a stellar atmosphere is. It's also what an exoplanetary atmosphere is. So if you were looking at Jupiter, it's the same thing. Okay?
Mhm.
Now, the processes that are going on in this layer are really threefold. One is that the light can simply be scattered out of your line of sight. That's effectively the same thing that happens in the Earth's atmosphere. It's the reason you see a blue sky. And it's what produces the extinction as you have either sunrise or sunset. That's just molecular scattering in the atmosphere. It doesn't leave a particular signature in the spectrum. It changes the structure of the continuum because the process is essentially a continuous process. But within the atoms, because there are energy levels that are discrete, the absorption and emission at the atomic level has to occur at discrete energies. Depending on the way that, well, just to use kind of a three-level atom, let's just say this is what one might call a ground state, and two excited states. Okay? The easiest way of imagining what's going on is to think about what happens in a stadium if you start filling up the lower levels and then you have people who have to walk up flights of stairs to get into the upper levels. These are going to be less populated. That's in thermal equilibrium. I'm getting technical. It's probably getting late. What's happening in the atmosphere is photons that are coming out from the photosphere, if they have the right energy, can be absorbed. And if the atom is sitting inside a medium that has a high enough density, because each one of these levels has a finite lifetime, before this level has a chance to drop back down, that is before the excited electron returns to its lower energy state, if there happens to be a collision, then no photon is going to be emitted. Okay? The energy that was absorbed by the system is then redistributed to the gas, and what you see at that wavelength is a dark line. The more material you have along the line of sight, the darker that line is going to be. And that's the absorption process. So the first one, if you had, let's say, absorption and then re-emission without scattering, without a collision, then you would still see a dark line in your line of sight, but somebody else looking from some other direction might see a bright line. Here, you'll only see a dark line. Okay? The absorption is a direct coupling between the radiation field and the gas. This is making sense, I hope.
Yeah, we're all muted, but it does make sense.
What you see, the problem is that without this, understanding what to do with the spectrum really isn't going to make sense. The essence of spectroscopy is based on the discreteness of the energy levels in microscopic systems, be they molecules or atoms. It's the same thing. The complexity is different, but the process is identical. That if you have an absorption event, there are only two possibilities. Either you get a re-emission of the same photon, or you could get a cascade. That is, you could have something, again, to go back to this, where you have an absorption, but you have, instead of one photon coming out, you have a set of photons coming out. Okay, that's again, if the collision doesn't take place before this has a chance to de-excite. All Now, let me emphasize this. All excited states in atomic systems have finite lifetimes. These can vary depending on the rules for these combinations of transitions. Essentially, it's like having speed limits on the road, that some transitions are allowed and some transitions have such low probability that the lifetime becomes very long. So for lines that are called permitted, that means that they're easy to de-excite. The lifetimes can be nanoseconds. For those that are called forbidden, the lifetime can be actually seconds or even longer. Those are going to just sit there waiting for somebody to come along and kick them in the head. It'll take a very, very low density medium to not produce a collision that'll de-excite it without the re-emission of a photon. Okay? But if you've got permitted lines and all of the lines that you see as the principal lines in the spectra you were just looking at, all of those lines have lifetimes that are anywhere from tens of microseconds to nanoseconds. Consequently, in an atmosphere of a star, collisions are almost guaranteed to take place. And so you see in normal stars that have high enough densities in atmospheres like the sun, you see only absorption lines in the spectrum, hence the origin of spectral types. Okay? With the distribution of the lines, you also have another attribute of the atoms, except for hydrogen, because it's only got one electron. Every other atom can come in a variety of ions, meaning if the energy is high enough, you can start stripping the electrons. So, for example, if you take iron that has 26 electrons in its neutral state, if the energy exceeds like 7 volts, which means it's in the near ultraviolet, you're going to produce an ion. Iron 2 has 25 electrons. They're not distributed in the atom in precisely the same way that the original neutral species was. And so they're going to have a distinct set of levels, okay? But to produce that ion, you have to start with the neutral and ionize it, which means there has to be a radiation field sufficiently energetic that you can produce that. The easiest way to do that is make this photosphere hot, okay? But it could also be something that's irradiated by, I don't know, space lasers. There are lots of ways of producing very high ionization. But in this case specifically, you can imagine that there's a limit here to how high the energy can be and have the electrons still bound. And if you have an ionization event, what goes off is an electron, and what's left is the next ion. Okay? The spectroscopic notation, which you'll see in the literature, is 1 is the neutral stage, 2 is the first ionization, and then it goes on from there. The reason for that notation, by the way, is from the laboratory, that you start out in the lab, unless it happens to be a really hot day, with neutrals. And if you put an electric field across it or you shine ultraviolet on it, a new spectrum appears, a so-called second spectrum. Okay, that's all this means. The ion still has all of the electrons of the inner shells, but it's lost some of it's lost valence electrons. And so the rearrangement of the atomic structure gives you a different sequence of lines. Okay? All you need to know is that each ion has a unique sequence. So if you're looking at the spectrum and you have a set of absorption lines, you can go to a laboratory list and find a correspondence with those lines measured in the laboratory under different energetic conditions. And with that, you have the basis of the temperature classification in spectroscopy, in stellar spectroscopy. The important thing in all of this is generic. The existence of these levels is just the result of atomic structure. The connection between which ion is present and this is based on something very important, that stellar atmospheres like the Earth's atmosphere are in a mechanical balance. They're hydrostatic. You don't see outflows, you don't see accretion in stars like the sun. Okay, the sun has a solar wind, but you'd never know that looking at its spectrum. The photosphere is a surface of constant pressure, and the pressure simply decreases monotonically and systematically as you go farther away from the photosphere. Okay? Which means there's a run of temperature and density in the atmosphere. The lower part is going to be higher ions. The upper part is going to be lower ions. And consequently, when you're looking at the spectrum, you're actually looking through this medium, all of which is recorded in the spectrum. Okay? Looking at the relative strength of the lines then allows you to recover the structure of the surface and the atmosphere through which you're looking. All of that is based on this fundamental idea that, well, the simplest way to put it, I guess, is stars don't have walls. That always talking about stars, systems in some kind of a balance. The fundamental condition that determines everything about the life of a star is that outside of it, there's nothing. You don't have somebody standing on the outside telling the photons, don't go, go back, okay? Stars ultimately lose energy. That's why you're seeing them. So the boundary, the condition that governs the transfer of radiation is that if you've got a photon that's bopping around in this dense area, ultimately, once it reaches a low enough density, it simply leaves the star. And whatever spectrum is born by those photons, that remains invariant to your view. Okay, you see it as it was at the moment it reached some depth in the atmosphere at which the path length for another collision becomes effectively infinite. And you see it. Okay? If stars actually had some kind of a wall around them, this wouldn't be the case. And that's also the reason why the deep interior remains hot. You could say the same thing fundamentally about the Earth's atmosphere. The reason the temperature decreases isn't simply that you've got less mass up there. It can also cool. Okay? That the outer boundary condition for an atmosphere is there's space. And the only way that the star can lose energy is by radiation. Consequently, when you take a spectrum, you're actually diagnosing the physical conditions in the medium from which that light emerged. And that leaves an imprint because it has to traverse layers of progressively lower density in reaching space. Okay? All of that is the heart of spectroscopy, that the sequence of lines, the presence of the ions, and the relative strength of the lines is telling you what the object you're looking at is. Now, that's in the case where the surface is stationary. In other words, something like the sun that's in a pressure balance under gravity. The atmosphere is the same. It just happens to be compact. The sun isn't pulsating. Okay, it's got a surface that's convective, that's bubbling, and is generating noise, but those are just sound waves, and they don't really do anything. They're not moving the medium. They may jostle the atoms around a little bit, but who cares? What's important instead is that if you take stars in equilibrium, and it doesn't matter whether they're red giants or O-type main sequence stars, it doesn't matter whether they're in binaries or single. If they're compact enough, the atmosphere has a simple run of temperature and pressure. Okay? So far?
Yeah.
Now, the next thing to make life a little more complicated is that in the history of the galaxy, you synthesize the chemical elements. And you guys all know, you know this. You've got nuclear processes going on in the interiors of stars, and once in a while, these buggers spill their guts into the interstellar medium. They either blow off their outer layers, which we'll get to in a minute, either in nova-like events, if they're accreting, in supernova events, in planetary nebulae, or they just mix material from their interior. But over the life of the galaxy, the interstellar medium has been progressively polluted. And the products of nucleosynthesis are then distributed through the galaxy and subsequent generations of stars. This is something we know from this, actually only from the spectroscopy. Subsequent generations are have more abundant metal fractions than stars that were formed in the early galaxy. So if you're looking at something that has, let me see if I can put it in another way. Since the life, okay, this is something just to give you a feel for what's going on. If you've got two stars that have the same temperature, the same mass, let's say the sun. We know the sun is going to last of the order of 10 gigayears, 10 billion years. Now, that means that you could have a star like the sun that's 2 days old. It's not likely, but you could. Or you could have one that's 9 billion years old. And otherwise, their spectra would look basically the same because they have the same mass, they have the same radius, they have the same atmosphere. But one of those, having been formed only recently, will be formed from material that has the composition of the gas in the galaxy now, while the one that was formed 9 billion years ago was formed in an environment that was less polluted. Okay, so you'll see the same lines in the spectrum, but they'll be stronger in the star that has a greater abundance of the heavy elements than they will be in a star which is older. Okay, so if you can determine from the spectrum what type of star you have, and this is not the spectroscopy, it's going through carefully looking at which ions are present to tell you what the temperature is, then the lines that are stronger are going to be from the star that has a greater abundance of the elements. Consequently, we can determine from not only which lines are present, but their relative strengths, what the chemical history of the galaxy has been. For young stars that is massive stars that don't last for very long, maybe 10 or 100 million years. Those stars are going to be more metal rich than stars whose lifetimes, statistically, than stars whose lifetimes are much longer. So stars that are high mass, bright, luminous, are those which are those that tell us what the current state of the galaxy is. And the fainter stars are the lower mass stars are the ones that sample the whole history of the galaxy because they could be formed at any time during the entire history. Okay? So one of the other aims of spectroscopy is to sample a range of stars, a range of these tracers of stellar evolution and of galactic evolution to understand something from within our galaxy of the process of enriching and the interstellar medium and changing the composition of the stars over time. It's really the only way we can do that kind of archaeology. We can do it in our galaxy. And that's because we can see the individual stars, and also we can see the individual faint stars. But under the assumption that anything that you're doing locally is basically the same as everywhere else, the assertion that we can determine the history of our galaxy says, okay, it's probably going to be similar for the history of any galaxy. So we can start applying this to understanding the evolution of the universe, not in the broad sense of the universe and the intergalactic medium, that is the whole of space and time, but these tracers that are the galaxies that are riding on top of that expansion. Okay? So that's the other justification, broadly speaking, for doing spectroscopy of single stars, is to try to reconstruct the history of the population. Now, the other thing, so let me go to another screen here. So another is that if you've got stars in a binary system, then another use of spectroscopic analysis, which you can't possibly get from photometry, is the Doppler effect. That if you've got two sources that happen to be co-orbiting, then at different times relative to you, these are going to have different radial velocities. So the lines are going to shift in velocity. By looking at the relative amplitude, you can determine the distance of the star from the center of mass of the system. And then from that, you get the mass ratio. Now, why the hell you would want to get that information is, first of all, if you've got two stars that are bound to each other in orbits that are short enough that you might be able to do them in a week, these have to have been formed together. So understanding something about how to understand how the binary formed, it's very important to know how the distribution of mass reflects the process of formation of the binary. That can be done with spectra that have resolutions high enough to allow the motion to be detected. Okay, a way of putting this is that if you're sitting at the middle of the visible, like 5,000 angstroms, if you have a resolution of 1 angstrom, you're going to see motion of 60 kilometers per second. Remembering that the orbital velocity of the Earth is order of 10 kilometers per second. Okay? The higher the resolution, that is, the finer the ability to distinguish the lines and their wavelengths, the lower the lower the velocity you can measure. Okay? So again, one of the advantages of spectroscopy that you can't possibly get from any other means is that you can measure dynamics. This was essential in the first half of the 20th century. Everything I just said about mass, for example, of saying you have a bright luminous star and that's massive when it's burning hydrogen, or you have a star like the sun, or you have a low mass faint star that's red. All of that comes from binary systems. That you look at the spectrum, you see which spectrum is associated with which velocity, you observe the velocity amplitude, and that gives you the mass ratio. Okay? From that, you can calibrate which stars at which luminosity and which characteristic spectra have specific masses. So, for example, in that discussion of WR140, everything that's known about that system, because it is not spatially resolved, only the outer environment that it's blown off over the centuries is resolved, either by HST or by JWST. The system itself is known only by the spectra, that there are two stars in the system, and you see that because two spectra are shifting in velocity relative to each other. Okay, that's it. If you've got a double-line spectroscopic binary, you can determine the mass ratios, and if it's eclipsing, you can actually determine the masses, because then you know not just the ratio, but exactly that you are looking at them exactly in their plane. And so there's no inclination effect. The individual velocities can then be turned into not just the distance from the center of mass relatively, but to absolute masses. That's something that one can do with amateur spectroscopy. That, for example, WR140 or some of the other Wolf-Rayet stars, in periods of order a week, they're massive stars, their velocity amplitudes are like 100 kilometers per second. So if you have a resolution on a spectrograph of, say, a few thousand, so to use, not intending to do public relations, but if you've got something like a LIRES spectrograph that's produced by Shelyok, so something that has a resolution of either 8 or say 11,000, you can resolve motions of 10 kilometers per second with no problem. So you can distinguish, if you keep observing the system, its motion. Now, why you would want to do that in a continuing way is that if you've got a system like a Wolf-Rayet, just to use an example, you're losing mass from the system. The physical properties are changing over time, and they may depend, because it's an eccentric orbit, on where the two stars are in their orbits. You can see that spectroscopically. You cannot resolve that spatially. But that cartoon that showed the formation of the dust was based entirely on optical spectroscopy. Okay? That can be done continuing on an amateur basis with modest telescopes. In fact, just to give you an example, a couple of months ago at Haute-Provence, a group of my students were using an 11-inch celestron with a moderate resolution spectrograph, and were observing WR140 just for the hell of it. And they were able to not only resolve the lines easily, but they were also able to get the radial velocity relative to what was known about its orbit in 1 hour. It's not that faint. What I didn't mention is that, having grown up in the Stone Age, when we were still using photographic plates, something I'm afraid some of you might actually remember. Uh, this wouldn't have been possible. The CCD as a detector is the liberating device because it's an imaging system that has extremely high sensitivity, extremely high efficiency. They're effectively 100% efficient for the detection of photons. They didn't have windows. And they're imaging systems. And they can be rendered digital on detection, so you can manipulate the data. Okay, all of the images that you would see of spectra laid out as nice, colorful, two-dimensional things are completely useless. Those are just for visual purposes. You can take a spectrum with a CCD and have immediate access to all of the information in that spectrum simply by looking at the profiles of the lines. So let me show you some examples. That way I can be more precise. You'll have, oh, I should also warn you, I have a tendency to talk. So if this is going on too long, just, I would say throw something, but that's kind of difficult from 10,000 kilometers away. But let me know, okay? I don't want to abuse you at this time of night. So let me,
Will do, but you're just a phenomenally good explainer.
thank you. I appreciate that. Here. Okay, so I think I'm gonna have to actually go to a new share. Yeah. Okay, so here you see a spectrum. This, provided I can move. Okay. On the bottom is wavelength. This is going from about 3,700 angstroms to 5,000 angstroms. Okay, it's an absolutely calibrated spectrum. This is Vega. It's not, of course, visible at this time of year, but in typical hemispheric racist fashion, it was chosen as the photometric and spectroscopic standard because it happens to go directly overhead in virtually all of the Northern Hemisphere observatories. And so when we needed to have something in the sky that could serve as the standard relative to which all of the other stars could be calibrated, Vega was chosen. It happens to be the prototype of spectral class A05. It's a main sequence star. It's about 2 solar masses. It's got a surface temperature of order 10,000 Kelvin. And every line that you see here is hydrogen. Okay, except for these buggers, which are not noise. This is what I meant by the metallic lines. Okay, so zooming in, for example, so in these lines, all of these very weak, you notice, very, very narrow lines relative to the hydrogen are all lines of iron 2, titanium, chromium. These are ionized metallic lines. There's one line in this spectrum, though, that is very, very different. I'm just going to mention this momentarily. This line happens to not be from the star at all. It's from the interstellar medium. It's a calcium 2 line. But ignoring that, what you're seeing here is the lines that are formed in the upper atmosphere, so the ones that are formed up here, and then the lines of hydrogen that, because they're so bloody abundant, are formed over the entire visible path of the atmosphere, all the way down to this portion, which is the photosphere. Now, what I mean by that is if you've got a column of hydrogen, then there's so much of it that some absorption is going to take place throughout this column at this temperature. What's absorbing in the upper atmosphere is in a very low density region. That which is coming from deeper is in a very high density region. So the collisions and consequently the perturbations of these energy levels, the decrease in the lifetime, in effect, broadens this out. The result is you're actually, although it doesn't look like it, getting a profile of the run of temperature and density in this atmosphere. The wings of the profile are formed deep and they're sensitive to the conditions in the lower atmosphere. The core is formed high up. So what you're actually getting here is a profile through the atmosphere with one line. Comparing the individual hydrogen lines, because they have different strengths, allows you to put a sequence together that reconstructs the structure of the atmosphere. Once you've got that, you can say, let's say this is an iron 2 line that has a particular strength. We know the temperature, we know the density. That means we have a certain abundance, because otherwise the line would be either weaker or stronger at that temperature. Okay? The sequence of these lines tells you then everything you need to know about that atmosphere. From that, you have the only clue you're ever going to have, the only window you're ever going to have into the interior of the star. Because to understand the nuclear processing that's going on in the star, to understand what governs its lifetime and its luminosity, you have to infer the way the radiation gets out. The only way to do that is from the surface, that is, from this last opaque surface outward. Okay? We have the same thing. You could say it's the same thing as you have in the Earth. You infer the temperature of the core because if you have deep mine shafts, you can measure the temperature gradient. You can't see the core, but you know that there's a source of energy in there that's producing a run of temperature in the Earth's interior that's driving all of the processes that ultimately we see at the surface. But the only way we know about those is either to penetrate into the Earth or to measure how much energy is actually radiated from the Earth. Now, we can extend this through the rest of the spectrum. In this case, we have going out to H beta. So hydrogen beta, gamma, and so on. You see that the run of the flux produces a peak somewhere around 4,000 angstroms. But this is what I was trying to say before. This doesn't look like a black body. This isn't just a continuum that suddenly drops off. There are all of these absorptions. Okay? So to go to another example, okay. This is also a star. It's very different. You don't see any absorption lines here. All you see are emission. And it's not covering quite the same region as I was showing you before, but it's not that bad. This is H beta. And all of these other lines are not noise. These are real emission lines. Okay? What we've got here, instead, what we were looking at before is something that is a dense atmosphere where collisions are dominating and where there is some kind of a photosphere. This, we would say, is just the opposite. We can't see the photosphere here. This is effectively at zero. But instead, we're seeing low density gas that's emitting. It's not necessarily hot. This is another one of those fables that we grow up with, that you usually say, well, dense cold gas produces dark lines and thin hot gas produces emission lines. If you've got low density and you don't have collisions, then anything that excites the system is going to lead to a de-excitation and the emission of light. So looking at which lines are present allows us to probe in a transparent medium what the temperature and density are. In this case, one of the things that's important, let me shift the spectrum for a moment. So, yeah, where do I want to go? Oh, these are cosmic ray hits on the chip. So let me do something that you can, just to illustrate a remarkable thing that you can do with digital data. I'm going to median filter this, and suddenly the spectrum becomes clearer. Okay, that is, I just applied a filter on digital data that removed the spikes. And what's left, you see, is again a very complex spectrum with lots of emission lines, all of which are from species that again are metallic ions, except that these lines are what I call forbidden. You see them only under low density conditions, these very, very sharp lines. The broader lines are permitted lines, and this is hydrogen. Now, this happens to be a star that underwent a nova outburst in 2010, V407 Cygni, in which, like the Wolf-Rayet, you have two stars in a bound orbit, except one of them went into a nova state and blew off its outer layers. Those plowed through the wind of its companion, and that's what we're seeing here, the relaxation from that. It's not that different than exploding a nuclear bomb, a nuclear weapon in the Earth's atmosphere. You have a fireball, a shock, and then the heating and relaxation of the medium after the shock passes. This is the relaxation. Now, the reason I'm showing you this is because a couple of weeks later, the spectrum looked different. So to make sure I get the right one, okay? That's the spectrum a couple of months later. It's very different. You don't see as many lines. The medium is cooled down. It's relaxed. Now, the details of what's going on here are less important than the fact that this thing was bright enough that you could actually observe it with an 11-inch and even low resolution spectroscopy. This happens to be taken with a 2.4 meter, the Nordic Optical Telescope on La Palma. But the same thing could be done with a much smaller telescope. Not necessarily at this resolution. This is a resolution of 70,000, so something like 5 kilometers per second. But if you had a resolution of even 30 kilometers per second, so something that you could easily get with an off-the-shelf amateur spectrograph, you would be able to study the variation of these lines. Now, why one might want to understand that is that you're seeing a process that takes place in many different environments. When a supernova blows up in the interstellar medium, it's going to produce a spectrum like this, except the timescales are going to be thousands of years. Here, the whole event was over in 2 years. So we could follow the passage of the explosion through this medium and then see its relaxation. Why one might want to know that is that it's an example of feedback. One star is affecting the environment around it. If a supernova goes off in the interstellar medium, it affects the whole of the interstellar medium surrounding it out to distances of perhaps 10 parsecs. If the same thing were to happen in an ejection from a supermassive black hole in a galactic center, the time scale might be 1,000,000 years and the scale might be a kiloparsec, but it's the same process. So if we understand it in this kind of model system, we can then translate that into an understanding of much grander, much more energetic processes. The physics remains invariant, the environment changes. And again, this is something that you can only do spectroscopically. If you try doing this with photometry, you get no information at all. In fact, by this point, the photometry was genuinely boring. The system had already relaxed from the explosion. Nothing more was happening. Okay, another example is, let me just make sure. I need to check which spectra I have here. Okay. Just as one more example, because we just finished this study. So let me make sure this is okay. Although I would love to go into the details, it would probably take 2 or 3 more of your hours. So I won't go into all of the details. I'll just explain that this also is not noise. In 2009, we saw something that was a unique event for the time, although it had been predicted as a phenomenon. And it's the only event of its kind we've ever observed. 2 stars merged. 2 stars that were essentially ordinary stars, but found themselves so close that their envelopes overlapped, and the period, in an interval of about 5 years, these stars merged to the point where they heated their mutual envelope and blew it off. And we saw that event. It was known as V1309 Scorpio. Some of you may have seen the light echo that's so famous from HST of a system in Monoceros, the 838 Mon, is something that looks a little bit like a Hieronymus Bosch painting, that it looks like a football with holes in it that expanded over time. That was another merger event, but we didn't see the actual event. Here we did, because there was a light curve from this system that showed that you had two stars that were distorted and in a common envelope, sort of like a peanut, and orbiting each other. And that in the course of 4 years, the period decreased, which meant the stars were moving closer together. This was the first stage of that event, where the envelope was blown off and it was still so thick and so cool that it looked like a photosphere. Okay? A few, literally days later, this was the spectrum. A week later, this. A couple of weeks later, this. You notice that now there are more emission lines and you can see the hydrogen series. So you still have absorption. There's still something here that's dense, but now there's also extended material. There's emission. And about 2 months later, that was the spectrum. So let me do this as that was the spectrum. Just emission. But there was something underlying it. So what we were seeing here was an expanding structure, both a shell and also refuse that was thrown out of the system as it was merging. By observing the time sequence, we can reconstruct the event. We couldn't resolve these stars. They have an orbital, or had an orbital period of about 1.5 days. They were so close that they formed literally a common envelope. The class on one class of binaries, the W Ursa Majoris stars, show the same thing. It's like looking at a peanut that's orbiting, okay? But in this case, something happened that made the system become unstable. And the two stars started losing mass, which meant losing energy by blowing material out, which meant gravity was going to win, and they merged. This is something that happens in the history of the galaxy. It's going to produce nuclear processing. Effectively, it's like triggering something that's going to have the effect of a bomb. It's going to blow dust out into the medium. In fact, this star dropped 10 magnitudes in the space of a couple of months. And it went from a peak magnitude of 8 to below, 6 to below 14th magnitude. And it stayed there since 2010. It actually produced that much dust. Hopefully, this is going to be a star that's targeted by JWST for infrared observations, because it should be quite spectacular to see what the material blown out of the system looked like. But until then, the only way we can infer any information about this is spectroscopic. We saw a time sequence. Okay? These are just a few examples. The kinds of observations that you guys can make are valuable for many reasons. One is that the more who are interested, the more objects can be covered. And you can follow these just also for your own interest, but also because you have access to something that many of us just don't. The sequence I just showed you, this sequence of V1309 SCO was taken with VLT. To get this sequence with VLT, you have to compete for time. And the success rate for something like this is like, 1 in 6. So you don't have a real chance of getting the kind of telescope time to follow these objects for long enough that you can see what happens as they expand, as they relax, as they change, as they exchange mass, whatever the object is. Stars like the sun are just, well, spectroscopically, they're boring. They don't do anything. Novae, supernovae, cataclysmic variables, mass exchanging binary stars are things that change over time. And to follow these is to potentially reveal physical processes that snapshots just don't reveal. Okay? You have the possibility, if you get interested, of picking objects, getting interested in them, and following their phenomenology, especially systems that pick up or do things that are aperiodic. The physics of these objects is revealed by their time histories through the spectroscopy, because you've got lines that are present, which lines are these? You have their relative strengths that gives you information about the densities and temperatures. You put all of that together and you have the most important thing possible. You have energetics, which point directly to the source of the radiation you're seeing. So you can reconstruct the events. You can reconstruct the systems. If mass is being exchanged in a binary system, the way the lines vary tells you how that mass is flowing. Now, all of these are questions that have grown important over the years within the community. They're not the be-all and end-all, but they're justifications, I think, for why one would be interested in this stuff. It's not just that they're fascinating. You know that. You're astronomers. But it's that things vary. And when you have this idea that the universe is fixed and in equilibrium, finding out that there are these systems that are wildly beyond and outside of equilibrium tells you that the history of the universe not only includes violent events, but those violent events are responsible for important properties of the universe as we know them, as we know it. Okay? Again, with photometry, you just get the broad energetics. Here you have all the information laid out. It's just a question of excavating the details, and those one gets to know. Should I stop?
Okay, if I could do a quick follow-up. This is a fascinating example, and we do have spectroscopists in SDAA, and I think they're online, Frank Parks and Dave Decker, probably others. But assuming that you're observing, or I'm one of those people, I had my targets, I was collecting data, and then all of a sudden this particular phenomenon would come up. Would you announce it and put in a request for data? And then, we would contribute data of this sort. and maybe a forum to discuss, the physics and the results of this aggregation?
Yeah, this is actually something that's been set up by the AAVSO. There's also a group that began in France, the ARAS group, the Amateur Astronomer Astronomical Ring, a spectroscopic ring. These are groups that have not only message boards, but have alerts and have discussion groups. There's also the eruptive variable newsletter that comes out of the ARAS group, but also is picked up by AAVSO. And that comes out, well, not as regularly as it should, but it's about every 6 months and includes discussions of novae, symbiotics, supernovae, things that vary, and also notes and discussions of these sources. Yes, these are announced. The other is, I don't know if you all know about the astronomer's telegram.
Yeah.
Okay, so usually the appearance of a transient gets announced there. And one of the frequent last lines of an ATEL is spectroscopic or multi-wavelength follow-up is requested.
Huh.
That is again a two-edged sword. One is that you're contributing, but the other is that it gives the impression that you're just putting data in an archive. The reason I went through all of this was to give you a feel for what you can get out of this data. That is, if you're going to do spectroscopy, if you're going to do astronomy, you should not just want to do it because it's adding data to an archive, but to start learning how to ask the questions yourself so you can draw information for yourself out of the spectra and inform the way you're going to do the observations. Because after a source is announced or you have something that's coming up on one of the alerts, it doesn't mean that the discussion is going to be about what processes you're seeing and how to optimize your observing sequence based on what you're looking at. It's frequently just some discussion of what the status of the source is. Okay? When we were doing observations of this source, but also of V407, when I worked on Novi, one of the things that's essential is to figure out what are we bloody going to do next. That is, if we see a certain sequence developing, should we change our cadence of observations? Should we change to a higher resolution? Should we try to bring in another spectrograph or another telescope? Are we going to be able to follow this for a long period of time? Physically, what are we seeing? And then how do we optimize the observations so we can get the most physical information out? That means looking at the data, not simply reducing it, being sure that it's okay, being sure that you've gone through a sequence, but actually looking at physically what information it contains. That's what I'm trying to encourage you to do. That when you get involved in any of these projects, one of the things I've noticed is my colleagues in the community are delighted with your contributions, but they're in a sense intellectually exploitive if they don't also get you involved in the analysis and the explanation of what's going on. So one of the things I suggest is you get more used to doing that yourselves. That's why I was emphasizing the physical processes. I mean, that's where the science is. the collection of the data is a wonderful thing, but when you have something like this in your hands, you have a wealth of things you can understand, and it's valuable at all levels because of that. And I'll say again, this is something that photometrists just can't do. Although, yes, the collection of photometric data is equally important in understanding what you can learn from the time series, because ultimately the photometry is just that. The reason variable stars are observed is to get a time series in the different bands and then understand the dynamics indirectly by looking at the way the output changes over time of these sources. But when you merge the spectroscopy and the photometry, you're in paradise. The two taken together give you everything that you would want: the energetics, the physical processes, and the dynamics all at once. I hope that answers the question.
Yes.
Can you tell us more about the AAVSO? Looks like they provide a great infrastructure for helping us, but I think we're not taking advantage of it. AAVSO is under new direction. Can you
Yes.
tell us about, do they know about spectroscopy? And how do we get more people involved in the AAVSO? And what data should we actually be archiving long-term? And is AAVSO going to help solve that problem?
Oh, yes, actually, it's working very hard on that. There's the publicity. Lindsay Ward sent this, and just to show you, the meeting is going to be this year in Tucson in November, but the AAVSO site, and certainly any information you would want directly, just the email address here, Lindsay Ward, is the contact person for the AAVSO. So it's a membership organization. It's both those who actually do this for their lives and those who do it for their own reasons. I'm not going to say pro-am, but those who we'll say are research and academic. So it's across the whole community. The spectroscopic section is currently working on creating a database. We have people who are involved with the verification and validation of the data that's submitted. There are channels for the submission of spectra, and there are also sites for chats and discussions. So it's still in the formation process to actually begin an analog with all of the appropriate search properties that the photometric database of the AAVSO has. Part of the problem with setting up the spectroscopy is that you don't have the kind of standardization that you have with photometry, that it's still to be decided how the calibrations are going to be done, what kind of data needs to be submitted. But certainly by next year, all of this will have passed the alpha and beta test stages, and it'll be available in general. But if you go to the AAVSO website and you look for information about the spectroscopic working group, you'll find all of the information about the current development of the database. The other is the ARAS group in France, which is also an international group. It's a bit smaller, but these people have been doing observations for, in some cases, several decades. And there's a database mainly of eruptive variables, so symbiotics, novae, supernovae, and cataclysmics from Meudon, the observatory in Paris. In fact, all of this in France started because there was a group in Meudon that wanted to observe the BE stars, which are intermediate mass stars, also near the main sequence, that are rapid rotators and show emission lines, hence the E. They're variable irregularly. Some of them are some of them are binaries. Most of them don't appear to be. They show mass loss episodes. They show emission lines that vary over time. Most of them are not periodic, and the group at Paris had wanted to cover these densely over time because they couldn't. They didn't have access to the telescopes. And so a group of amateurs were recruited by education to get involved with this, and that created a database that now has been going for well over 20 years. The so-called BESS, BESS. Those are the principle. I don't know if the British Association has a spectroscopic group. I assume they do, but it's not on the scale that the AAVSO or the ARAS group have put together. So there'll be more information about this as it develops. We're still in the discussion stages for some of the details. But any of you who want to get involved, please get in touch with the AAVSO about this, or you can get in touch with me, and I can put you in contact with the people who are directly involved with the validation and entry of data in the database.
Dr. Shore, I'm fortunate enough to be part of the spectroscopic working group with Bert Pablo and everyone. You were at a meeting last week, I believe. I hope you'll be a continued participant in that, because I really enjoy hearing your perspective on things. Kind of bring us back down to earth sometimes. A question is, we're working on the standards for how we actually process the data, so a minimum standard so that the members submitting data to AV-Spec will actually have data that's usable by academics, down the road. And I guess my question
is, say that let me break in for a minute. Okay. One of the important things to consider when creating an archive is you have no idea in the future who's going to access it. The thing that's really important, I think, in the creation of the archive is its absolute uniformity and fidelity, because oh, damn it, it's like the line in Julius Caesar by Shakespeare, when they've killed they've killed Caesar, and Cassius says, how many times shall this our lofty scene be acted o'er, in states unborn and accents yet unknown? When we as astronomers are weird among physical scientists. We have a historical record that's important. Nobody gives a damn about reproducing, say, the Millikan oil drop experiment using Millikan's equipment. Okay, we know what the charge of the electron is, but if you want to know what Ada Carina was doing in 1870, you have to go back to the historical record, and that may be damned important in understanding the evolution of that source. So this is something I've been trying to get people to understand with AV-Spec, that this is something always constructed for the future, and for anybody. You have no idea who's going to access it. So it really has to be with that in mind, that it may be somebody who really knows what they're doing, professional or not, or it may be a complete lunatic. The phrase that I learned when I was working at in the HST project is that when you're making something foolproof, you have to think of who the fool is.
So I know when I began a couple of years ago, I felt like it was truly the fool. It's kind of fun, but so you would say that for those of us using relatively low resolution equipment like an LP 600 or whatever,
Mhm.
standardization would be of the processing, capture and processing would be probably the most valuable thing we could do. Is
And
that
also, one of the things that people frequently forget when doing spectroscopy is if you're doing low resolution, you're somewhere between high resolution and photometry.
Oh,
So it's really useful if you can do it to absolutely calibrate the spectra. There are enough standards now around the sky that you can observe those standards and use that to get absolute fluxes. If you've got that, you've done both photometry and spectroscopy simultaneously. That's something I would really encourage people to do, because with low resolution, you can do that. At high resolution, it's harder because it takes more time. And you're usually working with standards that are fairly faint for the ones that are set up around the sky. Most of them are fainter than about 8th magnitude. But if you've got a reasonable sized telescope and an ALPI, you can do a 14th magnitude star in maybe 30 minutes at most, to enough that you would be able to absolutely calibrate.
so?
The other- Sorry?
So absolute calibration of the flux would be a pretty good goal to work towards.
Yeah, I think so. That's the most valuable thing you can do. See, one of the problems we have with the photographic data is we can look at line profiles. Many of them have been scanned, so the photographic plates have been reduced to digital form. But we have no idea what the energetics were.
Yeah.
That's one I guess I try to beat this into my students. To have in your hands a CCD, a linear photoelectric device, and not worship that in the way that it deserves by using it as an absolute detector, it seems to me a crime. Yeah, I've committed that crime many times myself, but if you can, in addition, observe a standard and get the sensitivity curve, remove the atmosphere, you're doing something even more valuable with the spectrum. It's added value, but tremendous added value. It's, on the other hand, a bit more technical and a bit more delicate, so most people aren't going to do it. But of course, low resolution spectroscopy has its place. Depends on the object. If you have something like a supernova, where the velocities are 10,000 kilometers per second, the lines are smeared over the whole bloody spectrum. So high resolution is largely a waste of time. If you're doing something like a nova, where the velocities are an order of magnitude lower, then resolutions of 10,000 are very valuable, and resolutions of 1,000, like ALPI, are going to be valuable for the overall shape of the continuum, and maybe some of the banded structure. Every spectrum has value, no matter what its resolution. It's a question of what you can get out of that. Okay? So you kind of match the sources that you're interested in to the class of spectrograph that you have available. You're going to do cataclysmic variables, for example, low resolution's fine. Because most of the phenomena are going to be registered reasonably well, because in a cataclysmic variable, you have mass exchange and an accretion disk where the velocities can be 500 or 1,000 kilometers per second. So low resolution is just fine.
Thanks.
Other questions? Well, on the lighter side, Dennis Amon posted, on the funny side of spectroscopy, are there photon jokes? And if not, he has one. Dennis, you
Well,
there?
I guess the only one, maybe it's a kind of joke, is when I'm starting to teach radiative transfer, I usually try to get the students interested in the subject by saying, okay, let's think like a photon. If you were emitted, where would you go? And it's kind of a way of getting them to think about what the processes are of the interaction, but I wouldn't say that's exactly high humor. So what qualifies?
Well, well, I have one here. A photon goes into a bar and tells the bartender, "A drink, please." The bartender gives him a drink and says, "Would you like to make it a double?" And the photon says, "No, I'm traveling light."
There's a place in hell for you. The only
going
counter
to-
I can give to that is that I live in Italy, and so I watch Italian traffic a lot. And over the years, I've begun working on the equivalent of Newtonian dynamics for Italian traffic. So the first law of Italodynamics is that an Italian driving will continue in a straight line at constant speed until hit by a bus. That's basically a photon. That they are basically stupid, and once you set them in motion, they will continue literally in a straight line, unaltered in their frequency, until they hit something. And once you understand that, you understand the whole of spectrum formation, that it's just a matter of what gets in the way. So traveling light.
Mm.
I'm going to do my best to forget that one.
I think we're going to have to put your response to Dennis's joke in the SDAA archives.
But I guess it's that when I started in this business, I didn't have a spectrograph. I didn't even have a telescope as a kid. I mean, I grew up in New York, so if I wanted to see the sky, I went to the Hayden Planetarium. But when I first started as an undergraduate, I got introduced to it. When I was in high school, I'd read in a used bookstore in New York, Strand. They had a copy of the Harvard-Smithsonian Conference on Stellar Atmospheres. And I stood there reading it and decided I want to do blue subgiants and I want to do abundance analyses of them. And when I got to Stony Brook, I was directed instead to Johannes Hardorp, who had in his drawer spectra of a magnetic chemically peculiar star, Beta Corona Borealis, that happens to be one of the brighter stars in the sky. And I just got hooked on radiative transfer, spectrum formation, magnetic field structures, stellar evolution. The whole thing kind of opened up precisely because in this data, there was information about the structure of the outer layers of a star. I think there's something remarkable and beautiful about that. It's the only way we're going to be able to touch these.
Well, that sounds like a good summation. It's getting late here and you have a morning to get to. Yeah, are there any last questions for Dr. Shore? Okay, well, I'll go ahead and close the meeting. Steve, I really appreciate you doing this presentation for us.
Thank you for
I
your patience.
I think the AAVSO ought to put conditions like, you know, if you guys are on the Pacific, maybe you ought to have your meeting Saturday morning or something like that.
No,
But
this is why I teach in the afternoon. Being of the undead, I don't have to return to the earth in which I was buried until dawn. So I have a rule that I don't teach before noon, so there's no problem.
well, you're still very gracious to do this. You know, when I
Real
realized the mechanics of this, I was a little shocked. But I really appreciate it. SDAA really appreciate this. This is very instructive and great presentation. So thank you so much. Is there anything that we can do for you from San Diego?
Just if you have any comments or questions, or I can be of any use, right? I'm always around.
Okay.
It would be a pleasure.
Okay. Well, again, thank you so much for this. It was a great evening, and you just gave us a super presentation and a lot to think about, and a little bit inspiration on the spectroscopy side too. Thank you.
Thank you. Good night.
Good night.
Thank you.
Bye-bye.